let's put what we've talked about to good use here. So we've talked about triangular matrices, triangular matrices, and we've talked about how determinants of them work. And of course here, this is a 3 by 3, and it's not a huge deal, right, to do this determinant as is. But let's turn this into a triangular matrix and see what happens here. See, how much work we end up having to do. Okay, so if we're gonna start turning this into a triangular matrix, what we might want to do here is say row 2 minus 2 row 1. Or it goes to row 2, sorry. Right, row 2 minus 2 row 1 goes to row 2. Now remember, this row operation doesn't change the determinant, so we just say this determinant equals this one. Let's see. So this row is going to be 2 minus 2, negative 1 minus 2, and negative 2 minus 2. Okay? Now we're going to do row 3 minus row 1 goes to row 3. Oops. Oops. I guess we'll do this on the next line. Okay. And again, when we do this, this combination of rows doesn't change the determinant at all. So we can just do this. All right, so this will be 0, minus 3, minus 2. And now we can get rid of this minus 3. So this will be row 3 minus row 2 goes to row 3. Right? And again, this combination here doesn't change the determinant. So we get 1, 1, 1. 0, minus 3, minus 4. And then 0, 0. This will be 2 down here. All right. Now look at this. We have a triangular matrix. This one happens to be upper triangular. And since it's a triangular matrix, all we have to do is multiply the diagonals. So 1 times negative 3 times 2. So the determinant is negative 6. All right. So, we have to do some row operations, but it can save us from writing out the full determinant. Now, this may not be as big a deal for this particular matrix because a 3 by 3 isn't so bad. But when you get up to 4 by 4 and 5 by 5, and it can really start kind of, wearing down on you, that one, this trick becomes a lot more useful. So let's do another example of this. Let's say, what's a good matrix? Let's compute the determinant of, let's say 2, 3, minus 5, 4, 1, 0, minus 2, 4, minus 3. All right, let's try this determinant out. All right. So let's see what we can do here. All right. Now again, when we're going for triangular matrix, we don't need to go quite as far as a row echelon form. Now you can, of course, but we don't need to go that far. We can just get it triangular. So we don't need the ones on the diagonal. All right. We just need everything sort of below the diagonal, or if you prefer above the diagonal, to be 0. All right. So let's go ahead and try and work this out here. So if all we're trying to do is get rid of the things below the diagonal, here, to get rid of this 4, we can do row 2 minus 2 row 1. All right, goes to row 2. Okay. So 2, 3, minus 5. Here we got 0, minus 5, 10. And minus 2, 4, minus 3. Right? And again, this row operation doesn't change the determinant. Here, we can do row 1 plus row 3 goes to row 3. Usually we'd write this in the other order. So let me do that. Row 3 plus row 1 goes to row 3. So 2, 3, minus 5, 0, minus 5 and 10, and then 0, 7, and minus 8. All right. Now here, we have some kind of weird numbers going on. So if you want to kind of make it a little bit easier on you to figure out how to combine these, let's say for this step right here, this 7, let's turn it into a 5. We'll turn it into a 5 because then we can cancel these out really easily. So we can do 5 over 7 row 3 goes to row 3. Now I want to point out this step, isn't completely necessary. We could do 7/5 row 2 plus, or row 3 plus 7/5 row 2 goes to row 3. But just to kind of see a different operation in here, how would that work out? Right, so we're going to multiply 5/7 times this row. So how does that change the determinant? All right, so remember, if we multiply row 3 by 5/7, right, so this is 0, 5. Here we just kind of have to deal with negative 40 over 7. All right. So what happens now? Now remember, when we multiply a row by a constant, we multiply the determinant by that constant, right? But we don't want to change the actual determinant that we have, so we have to undo that change. So here, if we're multiplying a row by 5/7, we have to put a 7/5 out here so that we don't actually alter the original definition, or the original determinant, right? Okay. So now let's get rid of this 5 right here so we can make it upper triangular. All right, so here we do row 2 or row 3 plus row 2. Row 3 plus row 2 goes to row 3. All right, so the 7/5 hangs out here still. We have 2, 3, minus 5, 0, minus 5, and 10. 0, 0. Now we need 10 plus negative 40 over 7. I'll let you double check. That's going to be 30 over 7. Okay. So, this is great. Now, if you really want, though, I want to show you one more thing we can do with these row operation tricks. So, because I think these are quite neat. So this thing right here, this row, is a multiple of negative 5, right? So a trick we can do is we can factor -5 out of a row. Now again, we don't need to do this here, right? We can just multiply this diagonal together, multiply it by this 7/5 out here, and we're good to go. So again, I just want to show you sort of one of the things we can do in addition here. All right. So we can have 7/5. Here, I'm going to factor -5 out of this row, and then it just comes out of the determinant. So how does that relate to what we have here? How is this related? Well, it's related because what I'm doing here, the step here is kind of, it's exactly -1/5 row 2 goes to row 2. Right? That's sort of exactly what's happened here. And again, that -1/5 just comes out here as the reciprocal, so -5. Anyway, just wanted to show you kind of that's another option you have. You can factor constants out of a single row. Right? So now, when we compute this determinant, we have whatever constants are out here from our various row operations. And then we just multiply the diagonal. So 2 times 1 times 30/7. And let's see, what does this end up being? So these 7s cancel, these 5s cancel. This is -60. And there we go. All right. So there's lots of sort of interesting things that come out of being able to do these row operations. So just remember, so we talked about taking a row and multiplying it by a constant, how that is going to affect things. We've talked about, combining rows and how that doesn't actually change anything. And then the last thing, which we didn't actually do here, if we swap 2 rows, that just creates an extra minus sign on the outside. So every time you swap 2 rows, you just put an extra minus sign, or -1 out front. Right? That's all that comes down to. So in the next video, I just want to sum up some rules that this stuff sort of leads us to. But before I do that, I want to talk about why you might be interested in row operations instead of just straight up cofactor expansion. So why might that be interesting? Well, so there's a really neat table in the book here that I want to sort of share with you. So here, if we do it by cofactor expansion alone, versus if we do row operations. Right? And again, this is row operations that just to bring us down to a triangular matrix. Okay? Because once we have triangular, we just multiply the diagonal. So what we're going to talk about here is how many additions we'll have to do and multiplications we'll have to do, like individual multiplications and additions that we have to do. Okay? So if n is 3, we have to do at most 5 additions and at most 9 multiplications to turn it into a triangular matrix. Okay? That's at most. For row operations, we would have to do at most 8 row operations and at most 10 multiplications. Now, this doesn't make a great case for row operations yet, and that's because 3x3 determinants are relatively simple. Let's go up to n equals 5. So here, this is a 3x3. These are for 3x3 matrices. Let's look at 5x5. Right? We could have to do up to 119 additions and up to 205 multiplications. All right, that's a lot, right? Depending on what your matrix looks like, that's a lot of steps. Let's look at row operations. We could have to do at most 40 additions and at most 44 multiplications. Now hopefully you can start seeing the advantage. To really kick it into overdrive here, let's look at a 10 by 10 matrix. For additions, 3,628,799 additions, or 235,300 multiplications. That's a lot. What about row reduction? 330 additions, 339. Now, obviously, you probably don't want to compute this by hand, right? Like, if you had, like, the worst possible matrix, obviously you'd be here forever doing cofactor expansions. But row operations, well, you know, it's a lot better. Now, why does this matter? Well, think about programming, right? Lots of encryption things can be done with matrix multiplication. And so you're going to, have a program do this encryption through matrix multiplication. I want to point out that's at least what I have in mind is a fairly simple encryption. But think of, if you needed to compute a determinant there, you could have your computer do, several million operations or less than 1,000. So, obviously, if you're doing something really complicated, you'll have much more than 10. But the point is, these row operations turn it into a much more efficient operation because you leave out a bunch of the multiplications that you would normally have to do. All right, so I'll leave that there. See you in the next one.